In this video, we will go through the Task2b from the exam spring 2020. There was one task with related to load flow. So this will be a tutorial on how to solve this. Of course, the exam and solution will be out in the canvas. Here you can see the grid system. It consists of 5 buses. 2, 3, 4, and 5. For now, it's bus 1 is defined as a slack bus, and we know now what that implies. We have also given a table for bus bar loadings. So the thing now is that we, for now, all the buses are defined as load bus bar. We'll come back to some voltage bus bar a little bit later in this task. I will mainly go through the every part of the this exam, but I will also add a little bit in the end. Yeah, this table you have loadings in megawatts and megawatt volt ampere reactive, P and Q. So it's given. And then the line parameters is given. So here you can see the from bus bar and to bus bar here and from. And then the Rx and susceptance are given for each line. So in the first sub question, we want to draw the Y bus. And we know that this, as I said, is 5 buses, so we know already that this would be a 5 by 5 matrix. In addition, the task wants us to calculate the Y33 with or without the shunt line admittance. So it's just probably just to see that you are aware how we do it. You should also indicate in this Y bus which element becomes 0. Then finally, you're going to calculate all the Y's admittances connected to bus bar 3 here. So let's first start with the elements becomes 0. Then we know that every element in the matrix becomes 0 when there are no connection between the buses. For example, this 0, down here you can see the complete admittance matrix when it's ready. And this is the Y, oh sorry. This is the Y5, 3, column 3. And as you see, this is 5, and there are no connection to 3, so it becomes 0. So you just go through, okay, let's check for the first row, 1, 2, 3, 4. So there is no connection between 4. Yeah, that's correct. No connection here. And so on. So you just go through and fill in the zeros. Let's continue to see on some of the elements of the matrix. For example, if we calculate the let's see, Y31, like this. So this is just 1 divided by set. Then you can use this relationship as you see here. That's a way to calculate. Now you also know that the off-diagonal element should be negative, so we can say that Y31 equals Y13 equals minus y31 equals minus 3.42 plus j 7.53. And this we can see in this matrix. So 3, 1 position is here, and then 1, 3 is here. So they becoming then similar. So you can see this structure into the system. So if you see here, this become 1, 2, 1 and 1, 2. So this is the off-diagonal elements. The diagonal elements we know it's the sum all connected to that bus. So if you take 4 y 1, 1 is equal to, let's see on the figure, connected to 1, 5 here, and 1, 3 here, and 1, 2 here, connected here, here, here. So then it's the sum y1, 5 plus y1, 3 plus y1, 2. Yeah, and just fill in and you will get the value 10.95, 25.9. And remember that this is plus value now, and the off diagonal is negative. Now calculate for y33. That was actually the task. It will be y31, 2 plus y34 connected to the bus bar 3. That will be the 10.47 minus j. And then now we have just the line admittances when we have also the shunt. That is also something you should calculate here. Of course, if you have a MATLAB program, it can do that for all of it very fast. But when you question this by hand, we typically just give you one small test just to see that you are doing the correct thing. y33 equals 10.47 minus j 23.15 equals, no, sorry, now I go fast. You of course need to sum then use the pi equivalent. So it's like a half of the susceptance plus j 2 plus b3, 4 on each line, half of it in each end of the line, and that gives a value on 10.47 minus j 23.11, like this. A little bit smaller value on the complex part. So now we have, see if we've done everything. We should draw the y-bus size. We should calculate the y33 with and without shunt line admittance. Indicate what element becomes 0, yes. And now calculate the y-connected admittance to the bus bar. Yeah, so if you have calculated then I didn't show you this, you have done it. The next subtask was to draw a flowchart to describe the Gauss-Seidel process. Here is like open is more the way you choose, you can decide, but this is like a solution I think is like the minimum you should show. So you start with the input parameters and form the y-bus in the top here. And then, of course, you calculate this power complex conjugate SK, VK, and also the sum of the impedance of voltages. So you know all the currents in the system. Then you calculate the new voltages, v key new with this expression here, and then you are checking is the new calculated voltage equal to the previous value. If it's yes, then it has converged, solution is converged, and you can then calculate the best pair conditions and line flows and so on. However, if you have no, then you go up again and do a new iteration based on your previous solution. So the third is to calculate the first iteration of voltage bus to the V2. So then just follow the process we just described previously. So first we calculate the current here, this form. Then we need to calculate the voltage at bus 2, 1 divided by 2. Cannot be 2 by J. Like this. Put in some numbers. Almost 0.9, I think. Then we put in the current 0.4. Just like this. So we are now need to calculate this to get a new value. So let's do that. Down here. GJ. The sum, of course. Equals. So then we just start with we start with j equal 1, so y21 v1 first. Let's have those numbers. 3 plus 1 plus j0 flat start. Then the next one, 2, 3. 2, 2 is not there. Minus 4. 4, 1. Like this. Next 4. Position 4 minus 4. And position 5. Yes, things like this. That it will be approximately something like minus 11.67 plus 26.09. like this. So this needs to come in here. And if we do that, we get something like 0.988. The first iteration of voltage. I just indicated then the admittances over the different positions in the 4 with the 0 in the last part, so it can be identified. Now for the subtask 4, we are now introduced a generator at the bus 4. Before it was just load buses. So the question was not what is known and what need to be found. So you need to write up a table explaining the different types of buses. This is the bus bar conditions. You can see the table below here. So and here we have the bus bar definitions. You learned about that before. So bus 1 was slack. The other was actually load buses, but now we have the part that we have let's see, we have a PV bus here. Yeah. So and here you need to determine the reactive power and the voltage angle. For the bus bar 2, 3, and 5, you have to determine the voltage magnitude and the angle. So here calling them the PQ bus, PV bus, and so on. You should also remember that, of course, that the generator has this capability diagram. PQ, for example, so it has a Q max and a Q min. So just remember that when it's not like you can feed in as much as you want. It has a max min, and often you have to specify that in your load flow program before you start the simulation. Now I come to the final task, the task 5 in the exam. So now they are specifying that with the new generator at bus 4, show by calculation V2, Q4, and V4, and only first iteration. The question is the reactive power within the range of the generator, as I mentioned up here, and give an explanation. So it's not like if you can't feed in so much reactive power, of course the voltage will fall at the bus typically, or it needs to draw from another buses. Some literature actually use some notation like this. I will just show. It can be useful when you work with Cartesian coordinates. Let's see, just y, k, j, v, j equal sum. And then we can write j, b, j. So we know that admittance work with conductance and susceptance. And the same way we can also do that with the voltage. So some notation are actually providing EJ plus JF. Okay, like this. Which this is the total VJ when you work with the Cartesian coordinates. And then this is the real part of the voltage. This is the imaginary part of the voltage. So when you see I'm using that now, then you can refer to what I'm actually meaning. In the book, we on the right hand side, I now put out the equations from Gauss-Seidel when you work with the reactive power and the voltage control bus. So this is how we define it here. And when you want to have the bus M, we have the reactive power. We take the imaginary part of the total S, you can see here. And the formula 742 is, of course, the way you use it when you have several iterations. So if you want the iteration K, so the QM is evaluated at the best previous voltage, as we say. And you're using then, this is the previous voltage, and also here. So just keep track on this. So you put this into the 740, the voltage calculator via K, and to find a new value of the VM, the bus M. Okay. So for this, just try to go through the example 7.7 in book. However, I will use a little bit different notation now. So I will further work on this EF I'm talking about here when we calculate. So in this case, on the right hand side, there was the bus M, was the bus we are evaluating, and the other buses is from J equal 1 here to, for example, M minus 1 plus N. From M to N. So this is how you can do it. Just keep track of the different notations. So let's go further on this notation. Let's take here. I'll just write out SK using K now. Yeah, this is the same as we have in 24, just using different notation. And then this can be written again as this again can be written. So now here, here, here. Let's further EK. Like this. Then just multiply it out. Then we take in the imaginary part, this equation here, so QK. like this thing. Yes. I can just say that the flow chart now for the Gauss-Seidel load flow is the same as before. However, we have to check if it's a generator bus. And if so, we need to include that in your evaluation. So what we can say is that if you have this, and the question is it a generator bus? And it's taking no here, like this. And then we continue on this path of Gauss-Seidel. This calculate VK new. You see on the previous. But if we get an yes, we need to check something. We need to calculate QK, and then we need to evaluate QK larger than Q max. Because the generator has a maximum. Then if it's yes, we can say that QK is equal Qmax, like this. And if we say no, then we will have QK less than QK minimum. That's the next question, like this. And if that is yes, then we put, oh, that was too small. Let's take it again. Then we put QK equal QK min, like this. So yes, then this we will continue calculate, and the same also we will continue calculate, because now we decided the constraints, the border from this if you outside the limits. And also if you get a no here, oh sorry, you get a no here, you also will continue on the algorithm. So mainly before just in the generator bus, you have to check this calculate reactive power and check if it's max min. And of course it will be oh, maybe black here. We need to do what we call if it's a gen bus. Again, highlight it. Yes, we should correlate it. VK equal VK specified divided on VK, like this. So yes, and then we go down and we calculate. We're checking as before. E key new equal old, see if it's converged. Yeah, then then you are back on track again. So what you can see is that we had to do two things with the generator bus. One is to go in this path on calculating the reactor power and checking max min, and also we have to do some correlation on the voltage here. I'll come back to that in the end of this lecture. Of course, I'm doing much more and telling much more than the you need to put on this exam, but I'll just give you a broader view on this. Okay, let's continue to calculate now the generator bus, and now let's put up the voltages firstly. V1 equals 1 plus 3 Cartesian, and then this V2 we know for now is 0.988 minus the 0.01. We calculated that previously, and then you also actually need to calculate the V3 in the same way as we did the V2. You get something like 0.987 minus the 0.01. And then V4 equal 1 plus J0. Let's start. V5 equal 1 plus J0, like that. So this is the voltage. So this will be then, in this notation, will be E1, F1, E2, F2, E3, F3, E4, F4, E5, F5. So just to keep in track on this. So when we now work with the bus bar 4, let's do that. Q4 would be minus E4 sum J equal 1 to 5 3 4 J plus E J. And this is due to that the F4 is 0. So that means this will be 0. And you can only work with this part. So let's write out equal, let's see, E4, sorry, minus E4. And then we will have 3, 4, 1, F1 plus E4, 1, E1 plus 3, 4, 2, F2 plus E4, 2. long expression. Then you just need to fill in all of this here, and the solution here is given for the exam. But here you can see all the details, how it's related. And it becomes really fast, really messy, and a lot of calculations. So very fast has to go to of course scripts and making in a computer solution with computers. So this will be then the value of 0.022636, very long. So now we are again ready to calculate for voltage for bus 4 finally, and I just made this already. Write it up like this. This is the same as previously for V2. Just keep track of all the numbers. So the only thing that we're missing now is this value, as also done previously, and we calculate that now. Then I also see that this misprint here in the solution. It's written 5 in the solution, but 4 is of course correct here, and the calculation is correct. So if we do it for then you calculate this y for j vj equal to -6. You have it in the solution, you can go through there, and plus j15, just try to wrap it up now, 0.5, and then v4 equals 0046 plus j 0.0 102 1 we can write. Now finally we have to scale these values here for the real and imaginary part. So we scale to meet the terminal voltage magnitude specification of 1.0 per units. And I've just written up now 2 ways to notation. So this is in the 743 in the book question. And with the notation used here in the presentation, we can see here on your right hand side. And then if we adjust this, we will come to the adjusted version. You can see over here, V4. So if you want the further, you of course to solve the whole system, you could now calculate the V5 voltage, and then you just repeat the whole process until some tolerance is met. And of course, this conversion, data system conversion, we could have also acceleration factor. This is all explained in the literature. Just like a weight you put on, so it will takes a bigger step every time it will do the calculation. That is something you could do. So with this, I will stop this lecture for now.